Section 5.4, indefinite integrals and the net change theorem. Indefinite integrals. Okay, indefinite integral f of x dx is the antiderivative of f. Thus, this means f prime of x is equal to little f of x. This antiderivative is not only a one function. Actually, this indefinite integral represents an entire family of functions. Okay? Okay. One antiderivative for each value of the constant c. Okay. Before, a definite integral was a number. But now, the indefinite integral is a function with a constant. So they are related with this fundamental theorem of calculus. Okay, here, yeah. Since the derivative of this function is x squared, so the integral x squared dx is this function antiderivative plus constants for indefinite integrals. The richness of the fundamental theorem of calculus depends on the availability of antiderivatives of functions. Okay, for example, integral secant square x dx is tangent x plus c, because the derivative of this is x secant square x. So so from those observations, we have the following formulas. For constant, coefficients can be come out, and additions can be. The integrals are linear and is homogeneous, and for homogeneous here, and is for constant, it's just kx plus c, and integral of x to the n is just this, because the derivative of this one is this. Since the derivative of this is 1 over x, so integrals can be written in this way. And the derivative of e to the x is itself, so indefinite integral of e to the x is e to the x plus constant. And all this, the derivative of this is cosine, derivative of this is sine. So derivative of minus cotangent is cos square of cosecant, and derivative of tangent is secant square. So those are all, since we know how to find the derivatives of this function, that means we already have the formulas for the integrals. Okay. Since we know the derivatives of many functions, we can easily draw the indefinite integral formulas like this. Okay. Okay. This example shows the general antiderivative of a function of f of x equal 1 over x. Since antiderivatives are different when x is positive and when x is negative. So the antiderivative can be written as the composite is the function on each intervals, on positive and negative. And indefinite integral like this can be spread like this by the linearity property, and by the homogeneous property, those coefficient constants can come out. So it became a very easy integration on each terms. So from the table, we know we can easily replace the values here to get the answer, which is 2x first plus 2 cotangent x plus c. Same thing. Find this one. Since we know this, the derivative of this is this. So we can easily find the antiderivative of the given problem. And for such, we can easily do the computations. Okay, so just, this is one of the simplest example that we have seen. And the next theorem also shows we just split it out, and then all others are okay except the integration of this one, which is involved in the arctangent. So we can easily find the answer on it. Okay, this integration can be done by a substitution, which we will cover soon after. And these are just simple integrals because we know the antiderivative of t square and antiderivative of square root of t and the antiderivative of 1 over t, which is ln of t. So we can easily find the answer like this. There are lots of applications of this. Lots of applications. Okay. 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 The integral over rate of change is net change. So let's take a look on the applications of the net change theorems. If dq over dt is f of t is the rate of change of quantity q, then this integral t1 to t2 f of t dt is a net change over this interval, which can be written as f of t2 minus f of t1. If this v prime of t gives the velocity of the moving object, then this integral means the displacement of the moving object. That's the changes between time t1 and t2. If an object moving along a straight line with a position function, then this velocity is the net change of the position or displacement of the particle during the time period. If we are looking for the distance traveling during the time interval, then this integration gives us the speed. And therefore, the integration of this one gives us if we are looking for the distance traveling during the time period with the speed, then the integral gives us the total distance traveled. So this integration can be used for many problems of real life, like this displacement, net change, displacement, or distance traveled, etc. So the integration can be found in various occasions. What it says, what this net says means both displacement and distance traveled can be interpreted in terms of area under a velocity curve, like this. The displacement is integral from t1 to t2 vt of vt is that should be the all of these areas, but integral from here to here gives us the only net changes. But since we are looking for the all distances or all areas, so we should give a negative sign of this value to make the whole area. So what we need is, in order to find the distance, we need to find the integral from t1 to t2 with the absolute value of v of t dt, which gives us this positive value plus this value is positive, and also this area with positive numbers. So altogether, that gives us the whole distance or whole areas that we were looking for. Here is the example, 6. A particle moving along a line so that its velocity at time t is this. Okay. Find the displacement of the particle during the time period from 1 to 4. And find the distance traveled during the time period. Okay. So, first question is looking for the just to find the S of 4 minus S of 1, because we are only looking for the displacement of particle. So all we have to do is just finding the definite integral from 1 to 4 of this v of t, which is minus 9 over 2. But when you're looking for the distance, what we need is the absolute value of v of t from 1 to 4, which gives us 61 over 6, because this graph changes its sign at 3. So it starts from the negative from 1 to 3 and then become a positive value on the interval 3 to 4. So we should give a minus sign on v of t on the interval 1 to 3, which gives us this, and just the positive value v of t on the interval 3 from 3 to 4, which gives us this and this, which sums up to 61 over 6, which is almost 10.17 meters. We measured in meter per second. So you now see the differences between just the displacement and the distance traveled. Only difference is giving the absolute value when you are looking for the total distance moving. And the last example is find the indefinite integral of this one. Okay. Here, if you do the computation, then here, this example 7 in section 5.4, for the variable x, we are looking for the integral of the function f, which is ln of tangent of x over sine x squared, which gives us this value. If you want to see draw the graph, then you can easily draw the graph. If we are looking for the other functions, so integral, then all we have to do is just change the number, change the functions as much as we wish. So if you just change the functions, then we can find the indefinite integral of the given function with this command. So basically, yeah, we can handle all the problems just to keep in mind the basic knowledge and the theorems. There are many problems in here that can be solved by the basic properties and the fundamental theory of calculus by using the antiderivative of the given functions. So you may try those with those property, or you can just simply use the computer algebra system to get the answers. Easiest way is to draw the graph and figure out what the theorem means, and then use any of the tool which is available to get the answer. After you get the answer, then you check it is reasonable one or not, whether it is in the domain or not. For example, the honeybee population starts with 30 bees and increase at the rate of T cube minus 2T bees per week. Then how many honeybees are there after 10 weeks? So we think the net change in population during 10 weeks, which easily can be found by the integrals from 0 to 10 to n of t dt, which is 2,400. So we started from 30 honeybees. So after 10 weeks, we have 30 honeybees plus the increased honeybees population, which is 2,400. That makes 2,430 honeybees at the end, something like that. So these integrals can be used a lot in many of the problems that you're going to face. Any questions?